So far this term, we've talked a little bit about kinematics and how the position, velocity, and acceleration of a particle is all linked together through time. In our last unit, we looked at how forces lead to those accelerations. So there was a really deep link between what we did in Unit 3 with forces and what we did in Unit 2 with kinematics. So we could figure out how to put forces on some object, and kinematics tell us how fast something is moving after some amount of time has passed, or how far something has moved before, how everything was related to us. We've got these forces, we've got accelerations, positions, velocities, all related to each other through time. But what we're going to find out in this unit is that while we were applying these forces to this object to make it move around and do things, we actually gave this object some new status, some ability to do something that it couldn't do before. And what we were actually doing was putting something called energy into the system. Now, I would guess that many of you are not physics majors. Some of you may be biology majors, some of you may be chemistry majors, some of you may be engineers, and the like. But energy is really kind of hard to define. It turns out which class that you're in tells you what energy really means as far as what we're discussing. So for example, you're in a biology class. What does energy mean? Well, you're probably talking about the mitochondria in a cell, the power source of a cell. If you're in a chemistry course, you may be talking about action potentials or something like that that leads to some reaction. And in a physics course, we like to maybe even take a little step further back, because there are a variety of different kinds of energy that could be stored in a system. But what we're going to talk about today is how to get something called mechanical energy in your system. Later in the term, we're going to talk about thermodynamic energy. Next semester, you're going to talk about electromagnetic energy and maybe the energy that's stored in light and the like. But what we would all probably agree with, regardless of our major, is that while energy may be difficult to define, it all is related to giving something the ability to do something that it couldn't do before. And there's lots of ways that we could give some element the ability to do something that it couldn't do before. Now, in each of these situations, whether we're dealing with cells, whether we're dealing with action potentials in chemistry, or we're really looking at mechanical energies from this particular unit in this term, energy is going to be a scalar quantity. Energy doesn't have direction. But one way that we put energy into the system is by applying, or at least mechanical energy into a system, is by applying forces. Force is a vector. And one thing that we're going to find is that we apply force over some distance, which is also a vector, to get this energetic scalar as a result. So the place that we typically start, okay, here we are, when looking at energetic systems is the concept of work. And we think to ourselves, well, yeah, I have been working all term. That's not the work that I'm talking about. And similarly, the way that we think about work and the way somebody that is maybe not a physics student thinks about work is really not the way a physicist defines work. So what is work? In a sense, a phrase to keep in your brain is force applied over some distance. Now, it turns out that not any distance is necessarily going to work, and not every force is necessarily going to work. But if we think in ourselves, applying force over some displacement or over some distance is how I can put energy into the system, how I can do work. And what the process of work is the ability for me to put energy into a system or take energy out of a system. And maybe those definitional words aren't terribly useful, but we can look at a picture. And from last unit, we know that if we had some block sitting on some table, there are a number of forces that could be applied to this block. Right off the bat, we know that the block has mass, so it's going to have some weight, naturally. If the block is sitting on a table, we know that the table is pushing on the block, so there's a normal force that's involved. And maybe what we wanted to do was try to move this block. So we tie a string to it and we try to pull the block across the table. This was one of the examples that we did when first looking at Newton's second law. It's something very much like what is pictured here. So we applied this force at some angle theta with respect to the horizontal. So what happens here is exerting a force doesn't do any work if the object doesn't move in the direction of the force, or some component of the force at least. So if I was to look at this block, sure, there are a lot of forces, and sure, this block is eventually going to move. It's going to get an acceleration to the right. As time rolls along, it's going to change speed to the right, it's going to change position to the right. All of those things are going to happen. So we see that something could be done. I could apply forces over some distance, but some of these forces aren't doing any of the work. The normal force is not in the direction of displacement. The weight force is not in the direction of displacement. And even in terms of the force that we are applying, only one component of that force is in the direction of displacement. So looking at this picture, what we're trying to do is look at the total net force here and dot it with the displacement vector. So sure, we have some force vector, and sure, we have some displacement vector, but the only time that we get work done is by taking the dot product of these two things. The dot product, we remember from Unit 1, is taking a component of some vector in the direction of some other vector. This is only non-zero if there is some component of shared direction. So vectors that are pointing in essentially the same direction have a large dot product. Vectors that are perpendicular to each other have zero dot product. And the reason we use the dot product is because this allows us to multiply two vectors but get a scalar out as a result. That's what we wanted, scalar energy. Now looking at this is going to have units of force times units of meters, which is a kilogram meter squared per second. This gets a special name in SI called the joule. And just at the bottom of this page, we can look at some scenarios. I could have some force that's up and to the right, and the block moves to the right. This is doing positive work to the system. It is putting energy into the system. But there's nothing that says we couldn't have a block that's sliding to the right, but I'm applying some force that's trying to slow it down. So this is a force that has a component opposite the direction of displacement, not in the direction of displacement. This is going to do negative work because the dot product of force and S in this particular scenario is a negative number. That takes energy out of the system. Energy that it did have is now removed from the system. And any time that I have some force that's perpendicular to the displacement, it doesn't do any work. So in this picture that we have above, the normal force is not doing any work even though the block is moving. The weight force is not doing any work, even though the block is moving. The perpendicular component of F isn't doing any work, even though the block is moving. Only that component of force in the direction of motion is doing any work in our system. Okay, so we think to ourselves, this isn't necessarily what I think of as work. So for example, I could envision standing against some wall and pushing against it. I could push against that wall all day and I'd start to sweat, my muscles would start to get sore, certainly, but that's not work. That may be exertion, but that's not work. And the reason why it's not work is not because you weren't applying any force. Okay, so I'm a physics major, right? So I don't necessarily have the biggest muscles, but I could certainly exert myself pushing on some wall. It's not zero work because I didn't do anything. It's not zero work because my muscles aren't particularly large. It's zero work because the wall didn't move. Because I'm not doing force over a distance, that's why I'm not doing any work. I still have force, but I didn't have any displacement. And that displacement is a necessary factor in figuring out what kind of work is being done. Now that's all kind of a scalar situation. It's the kind of thing that you might see in the algebra-based introductory course. But if we were to be a little bit more sophisticated about this, we could actually do this with calculus as well, because we don't have to have constant forces. We can have forces changing as a function of position, and that's perfectly and totally fine. What we are doing with our calculation for work then is integrating force over some interval of displacement, for example. So we're doing integrations like this. In fact, if we wanted to do this in 3 dimensions, there's nothing that says that force has to be a one-dimensional thing, say only in the x. It could be a force that has an x component, a y component, and a z component. And it could be a force that's different in all these different parts of space. And so then if we were wanting to calculate work, what we would do is take the force and dot it with some 3-dimensional displacement vector, and then integrate that from some point in space to some other point in space that they're all defined in a 3-dimensional space, but they're not defined in a 2-dimensional or 1-dimensional space necessarily. We don't have to get into those details here for this class, but that stuff is all out there. If I could figure out how some particular particle is feeling some force as I move it about the room, by doing the integral of how that force relates to the path that I chose, that tells me how much work I'm actually doing. And so if we were taking this primarily from this expression right here, we're using this kind of a thing to show what's going on. That's what's pictured right here. I could have some one-dimensional force. That force can be positive or negative, but it's a one-dimensional force. And if I was to integrate it over some range of displacement, that integral is telling me how much work is being done. And the way you do calculus, you're finding the area under the curve, right? So the way you find area under the curve is you break it up into the different parts and do that. But essentially all we're doing is very traditional, is all calculus that we completely agree, non-controversial calculus, right? Area under the curve, force integrated over some displacement. That's how we calculate what work is. And we're going to talk a little bit about this calculus stuff in just a little bit with an example problem. But what I'd like to do next, now that we know how to put energy into a system or take energy out of a system, it can also be useful for us to figure out, okay, well, once the energy's there, what is it and what does it do? That's a very valid question, because it's not necessarily going into mitochondria. It's not necessarily going into action potentials. It's not necessarily going into heat or sound or anything else. So what does it become? And in the case of mechanical energy, it typically takes 2 different forms. It can either be kinetic or it can be potential. And you may have heard these words, but what do these words mean and how do we go about using them? And we're going to start by looking at kinetic energy. So we know already that a force can be used to accelerate an object, right? That's what combinations of Unit 2 and Unit 3 were all about. We know that having an acceleration leads to changes in velocity. The way we get those accelerations is by having some net force. So if we could apply some net force to an object, its velocity is going to be changing as a function of time. And really, the velocity could be changing as a function of position as well because of that. So that being said, this leads to a mathematically interesting kind of behavior. So let's say I was applying force over some distance, and force is equal to mass times acceleration. This is net force in this scenario, even though there is no net sitting here. Using the definition of acceleration and a chain rule, what we're really doing is kind of taking the integral of mass times velocity over some range of velocities. And this is just a chain rule thing. So by taking the integral of this, the integral of mv is 1/2 mv squared. I have to put in my limits of integration. I find out that the work that is done is equal to the difference in 2 terms. A 1/2 mv squared that is at the end minus a quantity of 1/2 mv squared that was at the beginning. So what are these 1/2 mv squared things? And it's called the kinetic energy. The kinetic energy of some system is often referred to as 1/2 mv squared. So for very small masses, even large velocities can have a small kinetic energy, but as the velocity gets bigger, the kinetic energy goes up very, very rapidly because the velocity expression that leads to that kinetic energy is squared. So you double the velocity, the kinetic energy goes up by a factor of 4. Wow. If the velocity goes up by a factor of 3, the kinetic energy goes up by a factor of 9, which is almost a factor of 10. Wow. So the kinetic energy can really go up fast with this velocity. So what we essentially see in this equation right here is that the work that's done in the system is used to change the kinetic energy of the system. If you have some net work that is done, it will turn into kinetic energy, or it will take kinetic energy out of the system. And that's really based around the premise of the thing at the beginning. So yeah, I have this net force that creates an acceleration. The acceleration is applied for some certain amount of time or some certain amount of distance, if you're looking at kinematic equation number 4, right? Kinematic equation number 4 says that if you have an acceleration applied over some distance, that's going to lead to this difference in v final squared minus v initial squared. That's what kinematic equation 4 is all about. So, seeing these velocity squared relationships, that looks familiar. Having accelerations applied over some displacements, that's kind of familiar. This is really not too far removed from the kinds of things that we saw in kinematic equation 4, the kinematic unit in general. But now we've got a new name for it, the work kinetic energy theorem. If you can apply some net force to an object, that net force applied over a distance will change the kinetic energy of that system. That is the work kinetic energy theorem. And so you need a net force to do it. We could have my coffee cup sitting on the book like I've had many times before, and that coffee cup has forces on it. There's a weight force. There's a normal force on it. But there wasn't any net force on it. I know that because I could sit and look at the coffee cup just sitting there, right? It wasn't accelerating. So because there was no net force on it, it turned out that the kinetic energy of the cup didn't change. That didn't mean there was no forces. That means there was no net force. But then I could go about some scenario where I start pulling some block. I put some net force on it. That net force is going to be used to accelerate the block. That net force applied over a distance changes the kinetic energy of that block. And that's what the work kinetic energy theorem is really all about. So in this scenario with this block, I could push it to the right. And as I'm pushing it to the right, I see that I have a net force because of my finger poking on it. That net force applied over a distance will change the kinetic energy of the system. And because the mass isn't changing, and because 1/2 isn't changing, that means that the velocity must be changing. Similarly, I can use the work kinetic energy theorem to slow down a block. So maybe the block is moving to the right. It has some initial kinetic energy, but I start applying some net force in the opposite direction. It's going to take energy out of the system. Energy that was kinetic is now being taken back out of the system because I'm doing negative work on it. And if I was to push straight down on this block, maybe putting another block on top of it or something along those lines, but the velocity here is still to the right, because this new applied force is not in the direction of displacement. It doesn't increase the energy in the system. It doesn't decrease the energy in the system. And it doesn't really lead to any net work. There's no net force here. The normal force is now just balancing F and W, but there's no net force. That means there's no net work, which means there is no change in kinetic energy as this system evolves. A pushing down on the block like this can't speed up the block, and it can't slow down the block unless we have friction, and then all of a sudden this free body diagram doesn't apply, right? So that's what the work kinetic energy theorem is really all about. And let's say we were to look at a certain example here. This is just one that's worked out in the notes that we can look at very, very quickly. The case of a block that is maybe sliding on a plane here. So we've got this 6 kilogram block, initially at rest, is pulled to the right along a frictionless horizontal surface by a horizontal force of 12 newtons, shown here. Find the block's speed after it has moved 3 meters. And before we knew about today's unit, what we would have done is used Newton's laws to find out what the acceleration is. We would have then used that acceleration in a kinematic equation to find out what the speed is after it has moved some particular distance. So we're probably using kinematic equation number 4. And we could have come up with that new speed, right? What that would have looked like. What I have just described in words, we would use Newton's laws to find out that the acceleration, F over m, is 2 meters per second squared. F is 12 newtons divided by m, 6 kilograms, 2 meters per second squared. I would use that acceleration in kinematic equation number 4, and I find out that the final velocity is the square root of 2 times the acceleration times the distance that was moved. It's the square root of 12 meters per second. Okay, so we could do this problem, but I had to do 2 steps. I had to do Newton's second law, and then I had to do kinematics. One possible advantage here is that you can essentially do a similar kind of thing here by knowing something about energy and work. So how much work did I do by applying this force over a certain distance? So I did some force over some distance. I did 36 joules of work. Great. And in this scenario, if I started at rest, that means that the final kinetic energy is associated with that work that I did. So I can rearrange terms and find out that the final velocity is going to be the square root of 2 times that work that I did over the mass. That's just doing a little bit of algebra. And here we do that algebra and we get the exact same number, the square root of 12 meters per second. And so now I have to think to myself, in this problem, these 2 techniques were probably similar in effort from me to figure out. But I could see myself getting into some problem where it could be computationally difficult to start doing things like the calculation of what the acceleration is. Maybe the acceleration's not constant, and I can't use kinematic equations at all. Then I have to start thinking to myself, do I really want to do the calculus associated with finding the acceleration as a function of time, or finding the acceleration as a function of position, and doing the associated integrals to find out what the velocity changes are and the like? It could get really complicated fast. In the case of constant acceleration, yeah, maybe we're on the same boat. But what if acceleration is not constant? What if the force that's being applied isn't constant? Now all of a sudden these kinematic techniques and Newton's second law techniques are different. I'm not even exactly sure I could come up with some sort of problems that I'm not even sure I exactly know what to do with it. Initially, I'm sure you could come up with something. We can all do integrals. We can all do derivatives and the like. But man, it seems like it could be a lot of effort. And maybe I don't want to do that. And that's where these energetic techniques are really, really useful. We're going to end up doing, essentially in our next video, just how do we do the bookkeeping of figuring out where the energy goes? And because we're only keeping track of this scalar quantity, maybe that's going to be advantageous. Now this is just our first example. And like I said, it might not be intuitively obvious that it is terribly helpful. But what I would like to do is look at maybe something a slight bit more complicated. And that's going to be the problem that's shown here. So now we have force in the x direction with a magnitude f sub x, which is some number minus some number times x. And it's applied to a 6 kilogram box that is sitting on the horizontal frictionless surface of a frozen lake. F sub x is the only horizontal force on the box. And so if the box is initially at rest at x equals 0, what is its speed after it has traveled 4 meters? So one thing that often happens in problems like this is they're giving you all of these numbers. So like this 18 newtons minus 0.53 newtons per meters times x. Well, 18 newtons is just some number. It's a constant. this 0.53 newtons per meter, that's just some constant. It's just a number. The mass is just the mass. It's being applied over some distance we could call d if we wanted to. So there's a lot of constants that are coded into this that aren't specific to the details of solving a problem like this. So if I was looking at this problem, what I see is some force as a function of position. That's some constant, maybe we can call that alpha, minus some other constant, beta times, not t, x in this particular position. So alpha is just some number. In this case, what is it, 18 newtons? Beta is just some number, 0.53 newtons per meter. And we see that the units are going to work out, that the force is always going to be in newtons. But the force is different at every value of x. Another thing that we note here is that if we were to plot force as a function of position, this is a line, because it's linear in x, and this is just going to be some intercept. That's all that's going to be. So let's say in this problem, what it's asking us is how to do the work kinetic energy theorem to find out how fast this block is moving after it has moved some certain distance. Okay, that's fine. And we're going to do that, but it might also be useful to look at a couple of other things. So before we start doing the actual calculations here on the paper, let's go to Mathematica to get a better sense of what's going on here. So here we are in Mathematica, and we're wanting to look at the work kinetic energy theorem. So what we have here is that line. Alpha is some number. We can dial in what we want it to be. It's associated with the intercept of some line. Beta is associated with the slope of that line. Okay, so I can plug in beta to be whatever I want. For our problem, alpha was said to be 18. So I can put that in here, 18. There we go. And beta was 0.53. There we go, 0.53. The mass for our block, if it comes up later, was 6 kilograms, so we can plug 6 in. Okay, and now what I've done is set up this so that Mathematica will find the area under this curve and associate it with a change in velocity. Now, we don't know what that change in velocity is until we know the mass, know the position. There's some other things that are going to be involved. But we're going to be able to get answers and calculate them on paper later to confirm if what Mathematica is doing is correct. So in our problem, we were told that we were going to start at 0 velocity at a position of x equals 0. And we were supposed to find the velocity after some amount of distance has been traveled. I think it was 14 meters or something like that. So I can put 14 in here. We're going to find out that the velocity change should be something like 18.7 meters per second. Now, seeing a positive number here is associated with a positive area in this region. So say we hadn't gone over a very large distance, we only went over 2 meters, the change in velocity isn't necessarily very much. Then we go for another couple of meters. Now we're up to 7 meters per second. Now we're up to 8 meters per second, 9. Man, we're doing a lot of change in distance, but we're not getting a lot of change in velocity. This part of the curve isn't contributing very dramatically to this area. Interesting. If we wanted to, we could find out that, lo and behold, there's some maximum speed it gets to. If it starts at rest, by the time it gets here to 30 some odd meters, it gets up to about 10 meters per second. But now if I was to go further and further and further, it's actually slowing back down again, right? Because the force is being applied to the left to take energy out of the system. So initially force is to the right, speeding it up. Then force goes to the left to slow it back down again. So not only could we look at how fast is it going after it has moved some certain distance, and that's interesting, we could find out, okay, well, what is the maximum speed? How far does it have to go until it stops again? these are also interesting things that we could look at. And just using the Mathematica, we could get some pretty good guesses at what those are. So for example, this is going to be pretty close to its maximum speed, 10.1 meters per second. When does it stop again? We just go until delta V is equal to 0. That's going to be something like 68 meters, give or take. And that's just graphically what's going on with this. So going back to the problem, here's what we have. Force is a function of position that looks like this line. And what we are asked to find is what is its speed after it has traveled a certain distance. What I would like to do first is find work done by the force over this distance. So work is the integral of force dx. We happen to know what our force is. Alpha minus beta x dx, and we are going to be integrating it over some distance. We can call it d. So we're integrating from 0 to d, so to speak. Well, alpha integrated over dx is alpha x, minus bx integrated over is going to become 1/2 beta x squared, but we have to integrate it over these limits of integration. So this becomes alpha d minus alpha 0, which is alpha d, minus 1/2 beta d squared, plus 1/2 beta 0 squared. So minus 1/2 beta d squared. This is the amount of work that was done using the work kinetic energy theorem. This work must turn into kinetic energy. Sorry about the handwriting. So what we have found is alpha d minus 1/2 beta d squared. The work must be equal to the change in kinetic energy. If it starts at rest, this is the change in kinetic energy. So if you want to find out the velocity after it has traveled some certain distance, that velocity algebraically is this. And we know a lot of these things. So d for our problem is 14 meters. The mass is 6 kilograms. So let's pull out our calculator. We've got 0.5, we've got 0.5 times 0.53 times 14 squared is equal to this. This is subtracted from alpha, which is 18 times 14, which is this, times 2, divided by 6. Take the square root. So 8.17 meters per second. How does this compare with what we expected to see in Mathematica? back to Mathematica here. And we were integrating over the first 14 meters, so we can put 14 in. This is the integral that we were doing. It says 8.17, but you know, it would have been different for different masses. If things were light, it would have gone faster. If things were heavier, it would be going a little bit slower. But for our particular mass of 6 kilograms, this area was calculated as this thing we found on the piece of paper. So yeah, we got this right. This is what's going on. But now let's say we were also wanting to find maybe what the maximum speed is going to be. That is going to happen when we get to a force of 0, right? We're going to get that maximum speed that it gets to as the force disappears right before it starts applying negative force. It's going to happen right around here, right? So how would we go to the paper and look at this? So once again, we had force as a function of position. Looks like alpha minus beta x. And we are going to get to that maximum speed when the force goes to 0. So looking at this, what's that special distance where this goes to 0? So we're going to look for some special distance. And that is going to be alpha over beta. That's a special distance. If we were to put in a special position of alpha over beta, our force would go to 0. And in our problem, alpha was equal to 18 newtons. Beta was equal to 0.53 newtons per meter. Alpha divided by beta has units of meters. Pulling out our calculator, (18) divided by 0.53. So that special distance is about 33.96, or just about 34 meters. That's about where the force goes to 0. But now, what if I was to put this d, maybe I could call it d2, and put it back into our expression for velocity? So what is the velocity? In this case, it's the maximum velocity. That will be 2 over m. Alpha times d2, this special position where force goes to 0, minus 1/2 beta d2 squared under square root. Well, I could actually do a little bit of simplifying here, right? So sure, we have this 2 over m, but alpha times d over 2 is alpha squared over beta. And here I've got this 1/2 beta alpha squared over beta squared. So I've got this alpha squared over beta minus 1/2. This is 2 over m alpha squared over beta minus 1/2 alpha squared over beta. Two cancels with 2. Sorry. Got to keep track. So the alpha can actually be on top. And here I've got mass times beta under a square root, right? Let's get out our calculator what this maximum velocity is going to be. And we could have just plugged everything in and done it as well. But let's get out our calculator, clear everything. So mass is 6 times beta is 0.53. It's equal to that. Take the square root, put it in the denominator, times 18. 10.1, 10.09. That's our maximum speed. And this agrees with what we saw in Mathematica. What if we wanted to find out what position allows the velocity to go to 0 again? So we're looking at this, and I would like to find out, well, gosh, we could actually do an expression of figuring out where the velocity goes back to 0 again. But I know from the work kinetic energy theorem that when the net work that has been done is equal to 0, then the velocity hasn't changed. If it starts at 0 velocity, it ends at 0 velocity. So if we would like to find when the particle stops again, we can find the position where work is equal to 0. Again, going to Mathematica, we know that work here, this area, shaded area, is positive work, but this shaded area is negative work. I just need to integrate over enough of a range so that this shaded area and this shaded area are the same size, right? So if force is alpha minus beta x, and work from these previous pages looks like alpha d, I'll call this d3, minus 1/2 d, beta d3 squared. I want to set this work equal to 0. So work is equal to 0 if alpha d3 minus 1/2 beta d3 squared is equal to 0. I'm looking for d3. And I see that one position where this is equal to 0 is if d3 is equal to 0. It started at rest, started with 0 work. That's what that means. So taking that solution out of the scenario, we still can find one other solution for d3. And we'll see that that is d3 times 2 alpha over beta. And we know alpha and beta. So where is the position of d3 where this is going to stop again? 2 times alpha divide by beta, 67.9 meters. Which is consistent with what we see here. Very small velocity, and we could tweak in and get it ever much so closer. Now, there's nothing special about this linear force as a function of position. We could have had quadratic force as a function of position. We could have had all sorts of different polynomial forms of force as a function of position. Exponential forms, trigonometric forms of force as a function of position. There's nothing wrong with any of these things. But this is intended to give you some flavor of how do I take some possible word problem with numbers in it and write this in terms of variables and figure out what are some things that we can pull out of this. This was a non-constant force over a function of position. You can't use kinematic equations, even for this problem, because force is not constant, because acceleration is not constant. You would have to do the calculus for this problem. And this isn't as hard as it could be, but clearly it's not as easy as it could be either. This is not a condition of constant acceleration. So we know that net force could lead to changes in kinetic energy. But there's lots of times that I could come up with scenarios where I'm certainly doing some work, but it's not changing the kinetic energy of the system. So like in the case of my favorite coffee cup here, I could take this coffee cup and it's at some certain position. And it's not moving right now, no kinetic energy. And now I move it up to here. I have applied a force. I applied the force over a distance. Is its kinetic energy changed? No, it's still at rest. It was at rest here. It's at rest here. So I did work. I put energy into the system, but it didn't change the kinetic energy of the cup. So it must not have been net work. I must not have changed the net force on this. So in those scenarios, I can certainly find forces that are doing things that aren't changing the kinetic energy of the system. It's not a net force, but I can certainly have forces that do change the energy of some system. And from there, we're learning about the concept of potential energies. So if there's no net work done on an object, we can't change this energy of motion. But I can have forces that are applied over a distance, and they're not changing the energy of motion. Those types of energies are called potential energies. Okay? So if I lift an object to a new height above the ground, starting at rest, ending at rest, all I'm doing is changing the potential energy, not the kinetic. If I compress or elongate some spring, if I start from rest and I end at rest, hey, I haven't changed any of the energy of the system. Okay? So the first condition I want to look at is something called gravitational potential energy. Here what I'm doing is applying a force to lift an object up. So I'm applying a force up. I'm lifting the object up some distance, so this is force applied over a distance. That's how much work that I have done. It doesn't change the energy of motion. It gets stored. I'm giving the block the ability to do something that it couldn't do before. Fall. I'm giving it the ability to do something that it wasn't able to do before. Maybe you lift up a brick, and now I'm giving it the ability to crush a can when it drops back down again. So I'm giving it energy. I'm giving it the ability to do something. It took work and exertion for me to do that lifting, and this is how much energy that's associated with it. This is an energy of position, not an energy of motion. So it's important to note that potential energy depends on some reference position. Potential energy by itself doesn't necessarily mean anything. What's important is changes in potential energy. So if I was in some scenario where I used work to put a bunch of energy into a problem, and some of that energy might have been kinetic, and some of that energy might have been potential. Now all of a sudden, because all that energy is there, it can start to swap into different sorts of forms. What's important is not what the potential energy is, it's how the potential energy changes. It's not necessarily what the kinetic energy is. It's how the kinetic energy changes. Those are the things that are important. So maybe I can lift my cup, so to speak. I lift the cup and give it some potential energy. There was a weight force down. There is a force that I'm applying up. Here I have constant velocity, so there's no acceleration. Those forces balance. I don't have any net force that's applied. But I am putting energy into the system, potential. Now if I was to let go of the cup, the only force that would be applied is gravity. And so because of that net force applied over the distance as it falls, it would accelerate and change the speed of the cup, and it would hit the ground at some speed that's not equal to 0 and probably break, and I wouldn't like that. That's kind of what's going about on this page here. Now, that was a case of basically a constant force. The force that I have to apply to keep the cup lifted at this position, and at this position, and at this position, and at this position, they're all the same. You know, the force is constant, the accelerations are constant or 0 or whatever. But, you know, what if we were to look at some scenario where the force isn't constant as a function of position? Have we ever seen anything like that? And a spring is a good example of this. So if a spring is at some default position here, it doesn't feel any force. But as I start to elongate the spring, or as I start to compress the spring is going to respond in such a way as to try to bring that object back to a condition of what's called equilibrium. Huh. Oh, I'm looking at OneNote. You're not looking at OneNote. So I need to change it to OneNote here. So going back just a little bit, for gravitational potential energy, this is what I was talking about for gravitational potential energy. Here, what we're doing is applying force over a distance, okay? These are the notes that I was talking about. I apologize for that. I'll try not to do that regularly here. But I'm wanting to look at the case of springs right now. And the reason why I had Mathematica up is because what we were apparently looking at on the previous problem that we just did was a spring. That was a spring. So here, we have force that is linearly related to position. There is a position where force is equal to 0, right? Anything to the right of that position applies a negative force. Anything to the left of that position applies a positive force. It's trying to bring an object back to a condition of equilibrium at this position somewhere around 33 or so meters. So what we were looking at was actually the case of a spring. So that's what we have right here, okay? We can find area under this curve. That's essentially what we were doing before. But what we have with a spring is a force that is linearly proportional to the displacement. This constant of proportionality between position and force is something called K, the force constant for the spring. It has units of newtons per meter, just like we had for beta from our previous problem. So it works very much the same way. So if we're wanting to do work on a spring, what we are doing is integrating against this spring constant and displacement. But because force changes as a function of position, our integrals are a little bit more complicated. The spring energy that we're stored has a form more like 1/2 kx squared rather than something that is linear, some force over a distance kind of a thing. So this shows that we put work into a spring whether we compress or stretch, whether we make delta x bigger or delta x smaller. It's going to work in exactly the same way. Now in the terms of net work, maybe we pull on the spring and we're applying our force to the right and the spring is applying its force to the left and we're elongating the spring without changing the velocity. So there's no net work. I figure how much work I put into the system, 1/2 kx squared. The spring is putting in negative that because it's pulling to the left over that exact same displacement. So there's no net work that was done. But then if I let go, the spring force that's applied is going to cause that block to go back to the left again. That energy that I just stored in potential energy will get turned into kinetic energy in that scenario. And once again, this is not kinematic equations. The force is not going to be constant. The acceleration is not going to be constant. You really do have to integrate to find out how that energy that was stored turns into energy of motion. That's really how that's going to work. Okay, so this is really the setup to what we're going to be doing in the next video. So we've learned about how to put energy into a system and how to take energy out of a system. We found what energy of motion is, kinetic energy, 1/2 mv squared. And we found a couple of ways to look at energies of position, potential energies, one of them associated with lifting objects up, one of them associated with compressing or elongating brings. So in our next video, we're going to be using these different kinds of energetic forms to do interesting problems. So I'll see you then.